Hi and welcome back to Gaffy's Grinds. This is video 11 in our organic series on fuels for leaving cert chemistry. In this video, we're going to be taking a look at demand and we're going to be looking specifically at petrol. Now, every day, you and billions of other people cook with gas, heat your homes with kerosene, drive cars with petrol, get on buses and use transportation that uses diesel. All of these things, or by doing any of these things, you are using short-chained hydrocarbons. Now, because of the widespread daily usage, so if we say our short-chained hydrocarbons, so because of this daily usage, we have this disparity, okay, this widespread daily uses. We have a massive demand for these short-chained hydrocarbons. So the blue line shows the demand. But unfortunately, when we do fractional distillation on crude oil, we can only supply this amount, which means we have this big gap where we have to find a way to fill or meet this demand. So there were not enough short-chained alkanes produced by fractional distillation. Petrol was the fraction with the highest demand compared to its supply. So how do we solve this problem? So you might have already thought, can we simply mix some longer chain fractions like fuel oil? Can we take some of that extra fuel oil, mix it with petrol and dilute it down? It's a good way of thinking, but unfortunately it doesn't quite work. Now, when a high grade petrol, which is short chained hydrocarbons, when a high grade of petrol is burned in an engine, and I'm going to attempt to show this here, it is controlled by a spark plug. A spark plug is a little device which can create a spark. So this square box represents what we call a cylinder in the engine. And this rectangle, although it looks a rectangle here, would be a disc shape object. Sorry, I just need to draw that again. So it's a disc inside the cylinder. Now the disc is called a piston. And the piston is attached to another kind of a rod-like thing, which somewhere further down the road is connected to the wheels. And this piston can move up and down inside the cylinder. Now, the cylinder on the side has what we call an injector. And the injector injects fuel, a mixture of fuel and air into the engine. So these little droplets are fuel, and there also is air mixed in here in the engine. So air is required for the fuel to burn. Now, the engine doesn't do anything until the spark is created. So the spark plug creates a spark. Now, what happens when the spark plug creates its spark is you get this catching fire of the fuel. So the fuel catches fire. We say spark plug ignites the fuel. So ignition is when the fuel air mixture catches fire. Now this supposed to burn in a very smooth way. So the spark plug ensures that the fuel burns in a smooth way. So the spark plug creates the spark, and at that moment, the fuel in the area around the spark plug catches fire. And as it catches fire, it moves out in a smooth motion away from the spark plug, causing the next particles to catch fire. So it's like a wave of fire moving out from the spark plug, and it's very smooth. Now, the energy and the gases created in this combustion, this burning of the petrol, is enough to make the piston move downwards. So the piston pushes downwards, and the downward motion is smooth. It's smooth and it's regular. So it's not jittery. There's no vibrations. It pushes down nice and smoothly. And remember, what is burning, what is combusting is petrol. So in our engine, we have a petrol air mix. The spark plug creates a spark which ignites the fuel. The fuel then combusts, which means that it burns, and it burns with a smooth motion away from the spark plug. The energy and gases created push the spark plug down. This is with good high-grade fuel. Now, in the next step, what will this look like once all the petrol has been burned? Well, once the petrol has been burned, the cylinder or the piston will have reached the bottom of the cylinder, like I've shown. So the piston is now at the bottom of the cylinder. The spark plug is not sparking. So at this stage, there is no spark. So the spark plug is kind of like on a timer, which means it only sparks at precise moments. So it doesn't spark erratically just at any moment it wants. It sparks on like timed, like every, I'm not sure exactly how many seconds, but like it could be less than 1 second, but it's a regular time period. It sparks in a regular pattern. So when the piston hits the bottom, it then is going to come back up. And as it's coming back up, the injector is going to inject some more fuel. What happens then? Well, now it has left the cylinder ready to repeat its cycle. So we now have our piston back up. We have our spark plug ready to spark again. We have our fuel air mixture filling back up the chamber. And we have a new spark. And this piston goes back down and repeats its process up and down, up and down. Now, an engine has more than one cylinder, usually. Most engines have more than one cylinder, and these work together. As they go up and down, that motion is going to move the wheels of the car. Now, this is the process for what we call good petrol, or a high grade of petrol. Now, the question then is, what happens if we try it with poor petrol? So if we were to take what we said earlier, take some long chain hydrocarbon, like the fuel oil, and just water down or dilute down the petrol. What is the problem with that? Why can we not just do that? Well, there are reasons why that doesn't work. So here's our cylinder again and our piston. Okay, and we still have our spark plug. And we have our injector, exact same setup. We have our injector injecting fuel in. So we have our fuel air mixture again. So this is petrol, but it's a low grade petrol. So we're going to call it poor petrol. So this is poor petrol. Well, you still get the spark, just like before. And the spark creates this wave of combustion that moves out from the spark plug. But the issue with poor petrol is that some of these particles, before this wave before the wave of combustion gets to them, are able to spontaneously combust. Spontaneously combust just basically means that they don't need the spark in order for them to ignite. So they ignite without the spark. So we say this is called spontaneous ignition, or auto ignition. Auto means automatic. Auto ignition is what we call spontaneous ignition. So it's like imagining that you've got a box of firelighters for lighting the fire at home, and you've left them in the press, and they just decide they're going to catch fire themselves. So they just catch fire without you actually putting any spark to them. That would be spontaneous ignition or auto ignition. Thankfully, that doesn't happen with firelighters, but it can happen with poor grades of petrol. Now, these little miniature combustions, what they're going to do is they are going to have an impact on our piston. They are going to mean that our piston gets these little vibrations, and it starts to descend in like little shocks or little waves, and it creates this what we call a jittery motion. So it's not a smooth motion anymore. We say it's jittery, or it's like vibration. Now, so it's not jittery means it's not smooth. So it's not smooth like before with good petrol, and it's out of time. It's not controlled by the spark anymore. Out of time. Now, how would you know that this was happening? Well, it's often described as a knocking because it sounds like the engine is knocking. So the knocking bit refers to a noise that's made when you burn poor petrol. It's a noise that's made. So sometimes this is called knocking or auto ignition. It's called knocking. Now, what are the problems with knocking? Well, knocking can cause the engine to wear excessively, which if you have a new car and you're putting crap petrol into it, the piston going up and down in this jittery motion can cause it to scrape off the sides of the cylinder, and it can cause it to wear excessively as it goes up and down and not in a smooth motion. So it's supposed to be smooth. It can cause your engine to wear. It can also leave the car with poor power because, again, it's out of timing, and poor efficiency, which means that it uses a lot of petrol because it's auto-igniting. It's not behaving the way it's supposed to behave. Okay. Now, at this point, we have some questions to practice. So, actually, no, before we do that, we're going to just clarify some key terms here, some of the key words. Okay, so we've got one, well, we've definitely got one that I want you to, a keyword that we wanted to explain. So the key word is auto ignition. What is auto ignition? Okay, so what is auto ignition? Well, we have seen that auto ignition happens over here. It's spontaneous, and it happens before the spark gets to it. So before the spark causes this wave of combustion, these are already burning by themselves, these few particles. So that means it is premature. So like a child or an infant that's born before the 9 months is too early, it's born too early. We say it's premature. So auto ignition, we say, is the premature ignition or combustion of fuel or fuel air mixture before a spark is produced. This eliminates the ability of the spark to control the bus combustion in the engine. So that is what we mean by auto ignition. So I suggest now that you pause the video and take down that definition. Okay, right, from memory now, I'm going to get you to cover up anything that you took down there, and we're going to answer these questions. So I want you to do them from memory, cover up anything that you took down, and do these questions 1 to 7. So pause the video now. On 3, pause the video and do the questions. 1, 2, 3, go. Okay, so you should have now attempted to do those questions and the answers are coming up. Okay, so pause the video and make any corrections that you need to. Anything you don't understand, pause the video and go back and watch that bit of it again. Okay, so well done if you got those right. I'm hoping that you did. I'm hoping they're pretty straightforward after that explanation. Now in our previous examples, when we were looking at auto ignition, we talked about the terms good petrol and bad petrol. So I want you to imagine these two boxes contain, this one contains a good petrol, this one contains a bad petrol, or not a bad, poor is a better word here, poor petrol. Why is the one on the left good petrol? Well, if I was to zoom in and look at the molecules in here, I'm just going to draw the skeletal version or the skeletal formulas of the molecules. I would be seeing this. So what I am drawing here is I'm drawing different molecules or the different hydrocarbons that make up the petrol. I'm hoping that you have spotted some features here. I'm hoping that you have seen that we have lots of molecules that have short chains. I'm hoping that you have seen molecules that have branching. And I'm hoping that you have seen molecules that have ringed compounds. These are cyclic compounds. We've learned about these already. So ringed compounds or cyclic. Branching and short chains. The last one is an oxygen-containing compound. So these are the molecules that we will find in a good petrol. The problem, of course, is, like we discussed before, short chains and short little branch chains. These are not the kind of chains that get produced in the fractions of fractional distillation. We do get some, but not enough. If we had a poor petrol, this is what we would see. We would see more chains, more longer chain molecules. So poor petrols would have a higher percentage or a higher content of these longer chain molecules. They would have some short chains. They might have an odd branch chain, but they would also contain longer chains. So that would be the big feature of a poor petrol. Now, good petrols, therefore, what's good about them? Well, we say they are good at resisting auto ignition. They don't do auto ignition. That's what makes them good. So they don't cause the problems that we described above. So again, on 3, I wanted to speak to the screen. What are the problems that are created by auto ignition? On 3, 1, 2, 3. I'm hoping that you may have mentioned excess engine wear, poor performance and poor efficiency. So you use a lot of fuel to do a journey instead of you using less fuel to do a journey. That's what we mean by efficiency. efficiency. A high efficiency basically means you get more journey or more miles for the same amount of fuel. Poor efficiency, you get less miles for the same amount of fuel. You may also get a knocking noise when you've got auto ignition happening, something that we call knocking. So good petrols resist auto ignition. In other words, they do not ignite until the spark causes them to catch fire. Whereas a poor petrol does auto ignite. Ignite. Now, it is not enough to just say, okay, a poor petrol auto ignites, a good petrol doesn't auto ignite, because there's lots of different molecules in here. And to understand which molecules are actually responsible for the ability to resist auto ignition, we had to create what we call, we had to create a kind of a scale which helps us measure the different molecules' ability to resist auto ignition. And we call that scale the octane number scale. So good petrol that's good at resisting auto ignition, we say has molecules that have a high octane number. Whereas poor petrols contain molecules that have a low octane number. So the octane number system works off a scale. It starts at 0 and it goes up to 100 and it can keep going above 100. Okay, now to create this scale, we have to use two substances to create numbers at 0 and 100. And then everything else can get compared to these two substances. So the substance that gets an octane number of 0, that's really, really bad, that always auto-ignites, is this substance. It's got 7 carbons in a straight chain. So 1, 2, 3, 4, 5, 6, 7. And then it's just got all hydrogens. So this substance, what is it called? So on 3, figure out what that is called for me. On 3, 1, 2, 3. I'm hoping that you said heptane. You recognize that this has 7 carbons, so it's hept, and it's an alkane, so it's heptane. Okay, so you guys, well done if you got that right. You should know that. I expect you to know that by now. So heptane has an octane number of 0. This means it is a very poor substance having petrol because it auto ignites. To create a scale then, it goes up to 100. Something that 100 is considered a very good molecule to have in a fuel. We have a substance here which we give a reference of an octane number 100, and it's this substance here. 5 carbons in a chain, but sorry, I'm going to have to make a bit more space here. Sorry. We've got 5 carbons in a chain, so it's a shorter chain than heptane, and we've got 3 carbon or methyl branches. So this substance has a methyl here, here, and here. So the rest then are all hydrogens. Sorry. So what I want you to do is on 3, I want you to figure out what this substance is called. On 3, 1, 2, 3. Okay, I'm giving you a bit of extra time there because you might have to work this one out. Okay, think about the numbers and the branches. The naming system should be quite natural to you now. We did loads of these in practice. Well, what we've got is we've got 1, 2, 3 methyl groups. We've got a chain of 5 carbons. So parent name is going to be pentane because we've got 5 carbons in our main chain. We've got 3 methyls, so it's going to be trimethyl pentane. And then where are the branches? Well, we number the carbons starting with the ones which will give us the lowest numbers of the branches. So this is going to be carbon 2 here and carbon 4 here. So it's going to be 2, 2, 4 dash trimethyl pentane. 2, 2, 4 trimethyl pentane. So heptane, we say, has an octane number of 0. 2,2,4 trimethyl pentane has an octane number of 100. Now, other numbers are obviously possible. Anywhere between 0 and 100, we will have lots of compounds that have numbers, octane numbers in there. And also numbers higher than 2,2,4 trimethyl pentane, higher than 100, are also available. But these two were used as a reference to create the scale. So from 0 to 100. So there are some substances which are even better at resisting autoignition than 2,2,4 trimethyl pentane, and they go higher on the scale. Ones which are not as good at resisting as 2,2,4 trimethyl pentane, these go lower than 100 on the scale. Okay, so I hope that I have made that clear. So what features of molecules make them good or make them have a higher octane number? So what features? Well, it's the same ones that caused it to resist autoigniting up here. So if we can resist autoigniting in this mixture, it will have a higher octane number. So what are the things? So octane number affected by, how is octane number, or we say factors that affect octane number. Okay, so from memory, I want you to try and recall what are the factors that are going to affect octane number. We saw them in the features of the good petrol above. What will they be? So what I want you to do now is I want you to pause the video, and on the right-hand side of the page, like I have here, I want you to write down factors which affect octane number. Okay, so I'm hoping that you said, number 1, I'm hoping that you said shorter chains. Or actually not shorter chains, but chain length. Chain length affects it. And obviously, shorter equals higher octane number. ON stands for octane number. So you might have written that out in a more comprehensive sentence. That's fine. I'm summarizing. So the chain length is a factor that affects the octane number. Shorter the chain length, the higher the octane number. Number 2, branches. Okay, so if branches are present, if we have more, the more branches equals a higher octane number. 3, ringed compounds. Also affect octane number. So these are the main things which are going to affect octane number: the chain length, presence of branches, and the ringed compounds. Right, so what I want you to do is I want you to make sure that you have a record of that there. These are factors which affect octane number. And what I also want you to do is I want you to take down this scale. This is, we can call this the octane number scale. And it tells us the ability of a substance or a petrol or a fuel to resist knocking or to resist autoignition. And these 2 substances here are what we call reference hydrocarbons. Reference hydrocarbons. So they're what we use to reference to create a scale. So those 2, we need to know the number of them and which octane number they get. Okay, so what I want you to do now is I want you to pause and I want you to take a record of that there, the scale, the 2 compounds, their names, and their octane numbers. Okay. Now, it's time to do some practice. So questions coming up. Again, I want you to do them from memory, so you should cover up the notes that you're after making there. Okay, so cover up all the notes you're after making to practice these questions. These are the questions. Pause the video to do them now, please. Okay, so you should only be watching the video again if you have paused and you have tried to do the questions. Answers are coming up now. Again, if there's something that you didn't get and you don't understand, you can't see where I got the answer from, you need to go back and watch that part of the explanation again. Here's the answers. Okay, so well done. If you got those answers, I hope that you did. And I'll see you in the next video.